Hey, what's up, guys? Yeah, so previously I'm talking about the proof of Valiant-Vasarani theorem, and in this kind of proof that we need to introduce the idea called the independent hash function. Oh, sorry, the pairwise independent hash function. So pairwise independent independent hash function. Okay, so the basically simply speaking is that the following set you can write as a theorem, right? So following set, the following set H exists. Okay, so let me just repeat. So okay, so first one, so each H belongs to this capital H is a function from 0, 1 to the n to some, let's say 0, 1 to the k, okay, or however another set. And H is computable in polynomial times, or H is efficiently computable. So given X, H of X is easy to compute. Okay, number 3 is that the probability, let's say you randomly choose H belongs to H. So for all X, you pick any X in 0, 1 to n, the probability of HX equals to any number, or basically any number, or for all X, for all Y, the probability of H belongs to H equals to Y is very small, just universal 1 over 2 to the K. And then number 4 is that if you take X different from Y, then you want to ask, well, what is the probability of H over X equals to, and let's say you random for any X different from Y, and for, let's say, for any C and D, probability of HX equals to C, and H of Y equals to D, right? So you constrain on both, and you randomly pick H belongs to H is 1 over 2 to the K. Okay, once you have this, then you can prove the Valiant-Vasarani theorem just by using this hash function and converting this hash function into the set formula. Okay, and so in previous video I proved this. I didn't usually in some textbook that if you believe this is true, then you're able to prove the theorem prove the Valiant-Vasarani theorem. But seldom people talk about the construction of such function. So in this video, I will construct a special case. Okay. So in this video, I only prove the special case, but you can easily generalize this to general case. So I will consider H is a finite field. So I would say, let's imagine that this is FP and this is FP, some finite field. So I can construct this in a finite field, and you can generalize it into this more general setup. Okay, so let me just write down. So what I hope to construct is the following. So I say H is a function from labeled by AB. Okay, so it's very simple. How should I write? So HAB. Okay, and the HABX is defined with AX plus B, and then for all, so AB belongs to a finite field FP. Okay, so H is a function from and then by AX plus B, so it should map P, right? So H from FP to FP. Okay, so P is a prime. Okay, so obviously that by definition that these are like FP to FP, right? So this is efficient computable. So rest we are gonna to prove the 3 and 4. Okay. Okay, so 3, right? 3 is very maybe a little bit tricky. So 3 says something, right? 3 says that, oh, if I pick let's say I pick X, right, for X, right, and I pick C, so X and C are both fixed, right? And I want to ask what's the probability that I randomly pick AB, both AB are from FP, right? So FP squared, and the probability of AX plus B equals to C. Okay, hopefully this is 1 over P, right? This is what we're gonna do. Okay, so proof is very simple, right? Let's say suppose A0, then this term is the same as probability of, right, since A0, right? So whatever X I choose doesn't matter. So B belongs to P, what's the B equals to C, right? But I fix C, right? So B equals to C is just 1 over P. because I fix C, right? So I randomly choose B, so the probability B equals to C is 1/p. Okay, let's say suppose A is non-zero. Oh sorry, let's see. Sorry, I'm stupid. Suppose X is 0, right? If X is 0, then whatever I choose, it doesn't matter, right? So I only become like the same. Only if X is 0, then this is 0. So whatever I choose A doesn't matter. So the remaining is probability of B belongs to FP, the same as B equals to C is 1/p. Suppose X is non-zero, then we must have something. We must have this term equals to probability of choose A. Whatever B I choose, A must be 1/x, C minus B. Since this is finite field, right? So finite field, 1/x exists. So this is the same as I randomly choose B, and there is always a corresponding A. Okay, so it's just still 1/p. Because any B, I have only one A, right? So it's the same as I choose A corresponding to such B. So it's still 1/p. Okay, so combine these two. That's always 1/p. Okay, so we prove that. So you can imagine that this is 1/p. Still okay. Okay, so in the first results that I'm gonna to show that it is 1/p squared. Okay, so for any x different from y, for CD, probability of h belongs to h, h of x equals to c, and h of y equals to d is 1/p squared. Okay, so in this proof that should be very still simple, right? So I'm gonna to solve ax plus b equals to c, and ay plus d equals to ax plus b equals to d, and the solves a. Okay, and not so difficult. One can show that this is the same as, so you are solving these two equations, right? So let's say this is star, right? So the probability of star holds is the same as probability of AB equals to 1 divided by x minus y, 1 minus 1 minus yx CD, and AB. Okay, so I fix CD, right? I fix CD, and I fix x and y, and the x and y are different, right? So this, since x and y are different, so this exists, right? And this matrix is invertible because you can check the determinant is x minus y, right? So determinant is non-zero, so this is invertible. So we are just choosing the AB such that AB satisfies this equation. Okay, so the AB are independent, but both constrained by CD. So it's just 1/p squared. Because I fixed CD, there's only one solution which you can compute. You can compute this. You can compute AB by CD, right? So once you fix CD and then fix non-zero x and y, they always like 1/p squared. Okay, so now we have constructed such set, right? And each element belongs to set from FP to FP. Okay, and you can simply prove that you can change to this, to the power n. Okay, this is just by using the similar. You can use the inner products, right? You can define a tuple of FOP and combine it together. And yeah, I think the standard, yeah, you can use I think you can just change AX into AX. Okay, now each A is in FP to N, and X also in FP to N. Okay, and this is just defined to be sum over AI XI. Okay, and you can define your H A B to be AX plus B. Okay, and define such, and you can easily prove that in general this is also true. And maybe a little bit tricky point that you can make this to be like, in order to fix this to be higher, to be non-prime, but still it's not difficult. But you get a point that how to get this simplest pairwise independent hash functions.